Okay, so I posted this this article called "Gibbs Sampling for the Uninitiated," and this is kind of they use Markov chain Monte Carlo Gibbs sampling to perform a document clustering. I guess document clustering application or algorithm here. Okay, and so so the article it goes through quite a bit of stuff talking about just Gibbs sampling in general, but they do the application that we're going to look at is this idea of using it to cluster documents. Okay, and so so this is so I wrote up some handwritten notes here, and we'll just kind of walk through it, and I'll have you guys kind of write a little bit of code to execute this for your, I guess, last homework assignment. So I'm gonna post one more homework assignment, and we'll make it due sometime during 11th week, and this will be kind of your last assignment here. Okay, and again, Friday we'll have our final exam. Yeah, it sounds a little bit intimidating, but it's, well, I don't know. Of course, I don't think it's too bad, but you know, I'm biased in this in this regard here. So so the idea here is, you know, imagine getting a bunch of documents, and you read through them, and you want to kind of start making different piles. You know, one pile's about this topic, one pile's about another topic, one pile's another topic. And can we do this in some way that, well, I guess that can we kind of train a computer to do this? Even if the computer can't exactly read, can we still have the computer kind of create different piles of documents? Okay, so basically a document is just text. Documents can be something like tweets. Okay, you could treat each tweet as a document. Okay, those would be really short documents. Okay, or you could have longer documents where a document is, say, a newspaper article or a Wikipedia article or a book chapter or something like that. And what we want is we want the algorithm, we want this computer program to be able to kind of just read through it and group them, group similar documents together. We are not going to, and this is document clustering, it's unsupervised. So we are not going to define clusters on our own, okay? The algorithm will have to kind of discover these clusters by itself. Now, this is in contrast to, say, document classification. Okay, document classification, you have maybe like 4 or 5 categories already defined, and then you kind of feed it through, and then it would say, okay, based on what we see in the document, you know, we're going to classify it as this classification. But here we're just looking for clusters, okay? And so one thing is, because we are doing a cluster search, we do need to specify how many clusters to look for. All right, so you can say, so the simplest would just be look for 2 clusters, but you can also make it more complicated and say, you know, we want to find 10 clusters of documents or things like that, right? And so basically we're going to just have it read through, and it's going to try to group similar documents together. Okay, so document clustering is generally a harder problem than document classification. Again, with document classification, it's a supervised learning thing where the documents are already labeled to say this belongs to this class of document, and this article belongs to this class of document. But here we're just gonna see if it can try to make different piles out of these different documents. So we're gonna just start off with kind of a simple example. And we're gonna just say, let's try to sort the documents into 2 piles, okay? And how do we even use, what criteria do we use to say these documents should go over here and these documents should go over here, right? You're just kind of giving it a pile of documents, and it's going to, we want the algorithm to try to sort these two, the documents into 2 piles, okay? So a little bit of notation. We've got this fancy C. This is supposed to be, this is the corpus of all the documents. So let me just zoom in. So this would be this fancy C right here. This is the set of all documents. This is known as our corpus. And then if we put a little subscript next to the corpus, that will be all the documents with label 0, and C1 will be all the documents labeled 1. Okay, so you've got CX, all the documents labeled X. And so here we're just going to have label 1 and label 0. Okay, and then without the fancy, just regular C, C0 will be the count of documents labeled 0, and C1 will be the count of documents labeled 1. Okay, so I've got, so that's this, okay? The number of documents labeled 0 or the number of documents labeled 1. Okay, and the way we're going to cluster the documents is we are going to use a bag of words model, okay? The bag of words model, basically, imagine your document, right? You have all of these words written on a page, and imagine just taking scissors and cutting every single word out. Okay, so you take every single word and you just cut them out. And you take all of those little pieces of paper and you throw them into a bag. That's the bag of words model, basically, okay? Is that basically the identifying content of the document is how many words there are, which words appear, and the frequency that each of these words appear. We lose with the bag of words model is you lose any kind of meaning that's based on the structure, based on the order, right? So just imagine, again, the bag of words model is, imagine the article printed on a piece of paper. You're going to cut out every single word. You put all those words into a bag. And in the bag of words model, the order of the words don't matter. Documents are just what words appeared and the frequency of each word. So, so for example, one shortcoming of the bag of words model is that you could have 2 documents with very different meanings, but they're going to have the same representation in the bag of words model, meaning that they're going to be treated as exactly the same. Right? So one document could say, I am not upset, I am happy, okay? And then the other document could say, I'm not happy, I am upset. Now in both of these cases, the bag of words will say, am appears twice, happy appears once, I appears twice, not appears once, and upset appears once, right? So in alphabetical order, we've got we've got a total of 1, 2, 3, 4, 5, 6, 7 words. And those 7 words are broken down to am appears twice, I appears twice, happy once, not once, and upset once, okay? And both of them will have the exact same representation. So whatever cluster we assign these to, both of these will get treated exactly the same, even though these things kind of have different meanings, right? And so, so this is one objection I have for using a bag of words model for something like sentiment analysis. Sentiment analysis is kind of, they're asking, is the sentiment, is the kind of the general feeling of the statement. Is it a positive statement or a negative statement? Now, these two statements have clearly different opposite meanings, but with the bag of words model, they're going to get treated the same. And so, you know, I think for especially where words like not can drastically change the order or the meaning of the word sentence, this is not going to not a good way to go. Okay, but the bag of words model does work well if there is a strong link between words and subjects and topics. Okay, so for example, if you're at, you know, some kind of dinner party and just you overhear somebody use the word Bayesian in a conversation, just immediately your ears will perk up and you'll say, oh, are you talking about statistics or machine learning or something like that, right? Because the word Bayesian just only appears in certain contexts, and it will generally be in the context of statistics or machine learning or something like that. Okay, whereas other words won't have a very strong kind of link to a certain topic, right? So, for example, if you hear the word, I don't know, run, it could be in the context of sports. It could be in the context of cars. It could be in the context of, you know, computer program. You finally got it to run or something. And so a word like run is not going to have a very strong link between the word and the subject topic. Okay. So anyway, we're going to treat all of our documents basically as using the bag of words model. And with this, we're going to see if we can start putting these documents into different clusters. Okay. So this is how we are going to model the way documents are created. Okay. So we have a document creation model. And again, here we just have kind of, we only have two possible classes, class 0 and class 1, right? And so the idea here is you have some kind of Bernoulli trial in the beginning where pi is going to be the probability, okay, of getting, say, class 1 or class 0. And just for simplicity, we're going to say class 0, the document is about fruit, and class 1, the document is about sports. Okay. And the idea is each of these classes will have a different lexicon probability distribution. So if you think back to when we did when we were doing the deciphering, one of the elements that we had in as far as the deciphering algorithm went is that we had the lexicon. Let's see if I can open this. All right, and so if I have right, and so the lexical database had different words, and every word had a different kind of probability with it, right? We had 92,657 words, and okay, and each of these had, you know, different different probabilities here, right? So we could say, what's the probability of apple versus apples, or scores, or I guess we can get, there's no instance of the word scores, but goal. Okay. So right now we have different probabilities associated with each of these words. And the idea is we're going to have two different lexical databases, okay, or two different lexicons. So if we have the class on fruits, we're going to have inside this lexicon, if we were to add up all of the numbers, all of them add up to 1. But in the if the document is about fruit, words like apple and banana will have higher probabilities, okay? And words like ball and goal will have lower probabilities. Whereas if the document is about sports, words like apple and banana will have lower probabilities, and words like ball and goal will have higher probabilities. And so, so this part is going to be a multinomial distribution to generate our bag of words, right? So the multinomial distribution is like the binomial distribution, but it allows for the creation of multiple categories. So the multinomial distribution, it says, is a generalization of the binomial distribution. And basically it's, for example, it can model the probability counts for each side of a k-sided dice rolled n times. So it could be like, how often, if you generated, n trials or n words out of something, how often will you get? So we can, R is able to generate values from the multinomial distribution. And so we can say, R multinom, and we can say, what, I want 5 of these things. And the size, we'll say 10 words, and the probabilities are going to be a vector, vectors that add up to 1 to 1. So I could say 0.05, 0.05, 0.15, 5. What's the what is this? What does this add up to so far? Just left. It's 0.2. All right, so we got 5 categories here. In each sample, we're generating 10 random values, okay? So if you add up each row adds up to 10. Wait, what's going on? Oh, each column adds up to 10, sorry. Each column, 0, 2, 2, 4, 4 adds up to 10. 3, 2, 1, 1, 3 adds up to 10. 1, 2, 1, 3, 3. And so, well, this is interesting that just surprised that I'm getting so many of 0.05. So if I lower this to only 1%, this this looks a little bit more realistic. Okay. Well, I wanted to paint this. And I could say, okay, we'll generate 100 words. So if I'm saying generate 100 values out of 5 categories, and just kind of make it clear, maybe I'll say we only want to do like with these things. Okay. So we're going to generate 3 instances, 100. So again, subject to randomness, the first word appears only with probability 1%. So in a document of, say, 100 words, it appeared only one time. The next word appears with probability 19%. So in a document of, say, 100 words, this one appeared 18 times, and the second document appeared 23 times, and the next document appeared 15 times. And, this appears with probability 25%. And of course, because of randomness, maybe it's a little higher, maybe it's a little lower. The last one appears with probability 20%. And because of randomness, sometimes it's higher and sometimes it's lower. So these are just instances of, say, the multinomial distribution. It's just that in our case, rather than just having 5 classes with different probabilities, we might have like 90,000, okay? One for every single possible word. All right. Does that kind of make sense as far as what's happening here? So we're saying we're generating documents with a bunch of different words, and this will be kind of like our word count of how many times each of these words appear. Okay, so here's just me explaining the multinomial distribution. So the binomial distribution, you have n trials. Each trial has a probability of, say, a theta for success or failure. And if you did binomial with n equals 10 and p equal to 0.5, this would be, how many times does the coin land heads if you flip it 10 times, okay? And the conjugate prior for the binomial is the beta distribution. The multinomial distribution generalizes to more than 2 categories. And basically, you have n trials, and you have a vector theta, where the values in theta add up to 1. And here's an instance where, you have each of these things, and you're going to spin the wheel, and we just ask how many times does it land on space A or space B or C or D or E, okay? Except this time, we've got not just 5 categories, but say 90,000, one for each word, okay? And we're going to say the conjugate prior for the multinomial distribution is the Dirichlet distribution. All right, so if you think about the beta distribution always produced a value between 0 and 1. So if you had a beta distribution, say alpha equals 5, beta equals 5, it looked kind of like this, with alpha 500 and beta 500, still centered at 0.5, but it was a lot more sharp and pointy at 0.5. And if you had alpha 20 and beta equal to 80, it'd be centered around 0.2. The Dirichlet distribution, you now have a vector of kind of like pseudo counts for each of the different categories. So for the beta distribution, the alpha and the beta as these prior parameters served as kind of like pseudo counts for the number of successes and number of failures, because we only had two classifications. And now we have pseudo counts for more than 2 categories. So here we have a possible Dirichlet distribution. Here we have 3 categories, and we could start off with saying our pseudo counts are 2, 2, and 12. So in this case, category 1 will show up with this probability. Category 2 will show up probably all of them centered around, say, 0.33. Actually, this is drawn a little bit poorly, where each category, shows up with a probability between 0 and 1, okay? Whereas from here, the Dirichlet distribution, if my pseudo counts are 2, 6, and 12, a random draw from here, we will get kind of values where, 2 plus 6 plus 12 add up to 20. So 2 out of 20, we're going to expect something centered around 0.1. 6 out of 20 is, we're going to expect something centered around 0.3, and 12 out of 20, we're going to expect something centered around 0.6. So let me, I think I have to load line. All right, so here are, so remember when you do something like R beta, where you say, you know, I just want shape parameter 5 and 5, you can get values. So if I say 500, 50, 50, we're expecting values close to, say, 0.5, sometimes a little bit higher, sometimes a little bit lower, right? Because the beta distribution with shape parameters 50, 50, most of the values are going to be around 0.5. And so let me just show you what our Dirichlet, just to kind of emphasize, we'll do this 20, 60, and 120. Is off to, say, 3 decimal places. Okay, so with the Dirichlet prior distribution, a random draw from a Dirichlet is going to be it's going to be a vector of 3 probabilities that add up to 1. Okay, so these are the pseudo counts. So we're saying we've seen so far category 1 show up 20 times, category 2 show up 60 times, and category 3 show up 120 times. So what are the probabilities that generate this? So one possibility is category 1 is generated with probability 0.092, category 2 is generated with probability 0.314, and category 3 is generated with probability 0.595. Okay, if, another instance, we can get slightly different values. But generally, again, if you do 20 plus 60 plus 120, that adds up to 200. So 20 divided by 200, we're expecting something around 0.1. 60 divided by 200, we're expecting something around 0.3. And 120 divided by 200, we're expecting something around 0.6. But again, it's all subject to randomness. So it can be a little bit higher, it can be a little bit lower. Does this kind of make sense as far as what's happening with the Dirichlet? And so, you know, if I could continue this, and I could say, rather than 20, 60, 120, we could do 20, 60, 100, and 220. Okay, and so like 20 plus 60 plus adds up to 400. So 20 out of 400, you know, we're expecting something around 5%. 60 out of 400, something around 15%. 100 out of 400 is something around 25%. And 220 out of 400, what is 220 out of 400? Something around 55%. Okay, again, subject to randomness. So these are just different random draws. And again, you can see something. Let's click 10 of these things. And these are all different instances. And if you add up each row would add up to 100. And we're getting some kind of different kind of vector values here. Okay, so the idea here is we are going to use a Dirichlet distribution, not with a vector of length 3, but a vector of length, I don't know, 90,000 or something, okay? Of kind of pseudo counts for every single word in the, I guess, English language. All right, so if you think about our lexical database has, you know, 92,000 entries. And so we're going to, and maybe we won't go as extreme as 90,000 of these entries, but basically we're going to use a Dirichlet distribution to generate kind of the word probability vector. And then we're going to use the resulting word probability vector to say generate the actual word counts that we observe. And so this is our diagram that we've got. Okay, this these are the actual words. Okay, so WJK is the frequency of word I in document J. Okay, so this will be like, how often did the word apple appear in the first document? How often did the word banana appear in the first document? Or how often did the word ball appear in the second document? Okay, this will be a count. This count is generated based on the label of the document. Okay, so it's either label 0 for apple, for fruit, or label 1 for, say, sports. Okay, and depending on the label, we have a different word probability vector. Okay, we have a probability vector theta for, we have two possible theta vectors. We have the theta, the vector of probabilities if it was about sports, and we have the vector of probabilities if it was about fruits. So depending on which label we have and which theta, we are going to generate words here. Okay, the theta vector itself is based on the hyperparameter, or basically it's based on this Dirichlet distribution. Remember, this theta vector is based on the Dirichlet distribution that generates the words. Okay, so it's the kind of the multinomial prior, the Dirichlet distribution. That is how we're generating these thetas. Okay, whereas which label we select is just based off of a Bernoulli. Okay, we have, it says this gamma sub p. This is basically just the hyperparameters of the beta distribution, indicating whether we are in document class 0 or document class 1. Okay, so we are so as I guess part of your homework, you'll have to kind of read through this, but the idea is we're going to be generating using the Gibbs sampler. We'll try to sample back these unknown parameters, and so we have the model, and it is a hierarchical model as far as how these words are being generated. Okay, and once we have that, we can then go through and kind of count up the words that appear in each of these things. So let me see, we'll see all of these kind of different notations appear. All right, so the priors, again, we're saying as far as the documents come from, the document, whether it was whether it's about fruits or sports, that's a Bernoulli, okay? And the Bernoulli of how the coin flips comes from the beta distribution. All right, but then where do the thetas come from? Okay, the theta is the vector, and again, this is going to be a long vector. Here I only have, say, 4 values, but probably in our document system, you might have a vector of length, say, 1,000 or whatnot. Okay, here actually for the homework, I will tell you what you will be looking at two sets of documents. The two clusters are very simple. Okay, and this will make it very, very simple. Okay, so you're going to have a total of 19 documents. Okay, and for each of these documents, I took a couple pages out of the two Dr. Seuss books. One is Green Eggs and Ham, and actually Go Dog Go is not a Dr. Seuss book, published by the same company. It's written by P.D. Eastman. Okay, but anyway, Go Dog Go has the documents, the words are like dog, big dog, little dog, big dogs and little dogs, and there's pictures to go along with each of these things. But basically, when you go through this, if you see the word dog, it's a pretty strong indicator.
I'm getting a call. The headphones are saying I'm getting a call.
Okay, if it says dog, it's going to be a pretty strong indicator that it's going to be from from this cluster. Okay, versus if you see things like eggs and ham, it's going to be a pretty strong indicator that it comes from the other cluster, right? So the idea is if you were to just kind of see these piles of documents, okay, each line here being a different document, can we sort these into two different clusters kind of automatically, right? Without informing the computer that that one set is green eggs and ham, the other set is about dogs. Just can it pick it out based on the word counts? So we're going to turn each of these vectors of words into just word counts, and using those word counts alone, right, which were generated by these multinomial distributions with different word vector probabilities, we're going to try to sample back and identify which cluster each of these documents belong to. So in the homework, I'll get you started with some of these lines. There's a few text packages that we're going to load up. Okay, TM for text mining and Snowball for just kind of handling these words. I'm going to read in the words. Oops. Okay, so I'm going to read in. Clear this out. So you're going to read in these things. So it's a vector with all of these words. I'm going to just kind of combine them together. And I shuffled these up. Okay. So here I've got 19 documents. And the question is, they're all kind of mixed up now. And can we sort these into two different clusters? All right. So we have 19 different documents, and here I'm going to just create a data frame based on this. And so the data frame is just the document ID 1 through 19 and the text, okay, which is a bunch of things, right? I do not like them in a box, or a big dog party, things like that. And we want to kind of sort these. So one thing is we're going to create a corpus based off of this data frame. And this creates a structure called simple corpus. And this allows us to do So we can just say, you know what, let's take a look at one of these documents, right? So I can say document corpus item 4, and this is the thing. It says a green dog over a tree, a yellow dog under a tree, 2 dogs on a house, and a boat in the water. All right. And then for kind of the processing, there's a whole bunch of text applications. Okay. So one of these things is we can say, you know what, let's turn everything into lowercase. And so if you do that, it takes all of this text, a green dog over a tree, and it turns everything into lowercase, right? And then another one is we can say remove all punctuation and remove all numbers. So it removes all the punctuation. So it gets rid of all the question marks and the commas and the periods. And so now we just have words, right? And then one thing we'll do is we'll remove all English stop words, okay? And this is gonna just remove common words like a and the and stuff like that, okay? So here it is with the stop words in. And once I remove the stop words, it really shrinks it down, okay? So it says, it looks like it gets rid of a bunch of prepositions as well. So we have green dog, tree, yellow dog, tree, 2 dogs, house, boat, water, dog, things like that. So basically all of these articles and prepositions, it gets rid of them, okay? And then, you know, you don't have to do this, but you can also stem the document. And what stemming does is it turns words like running, runs, and runner, all of those just become run. So as far as this thing goes, it doesn't seem to make a huge difference, but it'll turn dog into dog, and dogs become dog, okay? And then house becomes house, H-O-U-S, because it allows for things like house, houses, housing, which would, so the stem there is H-O-U-S, okay? And so I don't, it's all internal to this TM package as far as, you know, how it stems things, and it does some weird things, right? Like goodbye, it drops the E, I guess, I don't know, goodbying, I don't know if that's a word, goodbyes or something, right? So it does a few things that are a little bit strange, but it'll stem them. So basically dogs and dog will get stemmed to be together. Okay, and then you can also strip the white space. And so, so this is what the document looks like at the end. And here's like another dog, another line, whereas I think if we look at the original line, it says a train, a train, a train, a train. Could you, would you on a train? Not on a train, not in a tree, not in a car. Sam, let me be, right? And what does it become? It becomes train, 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 train. Tree, car, Sam, let, and it just, you know, Sam, let me be becomes just Sam, let, and then it says, I would not, could not, right? So all of those words that make green eggs and ham what it is are considered stop words, which is unfortunate because you lose a lot of it, right? So this is the bag of words model, and, you know, getting rid of stop words really reduces it, right? And so it reduces the whole thing to just box, fox, will eat, house, will eat, anywhere, green egg, ham, like Sam, okay? So, you know, I think it's like, you know, I do not like them, Sam, I am, and things like that, right? But Sam, I am just gets dropped to just be Sam. So a little bit unfortunate. It's not going to be good for poetry, but just, again, we're just trying to classify or cluster our documents. All right, so you can take this entire corpus after we've done all of this cleaning and create the document term matrix. The document term matrix, let me just show you, goes through and it tells you, okay, document 11 has this kind of word frequency, right? So if I take, let me just kind of turn it into a word count. So this will be like document 1 has the word anywhere, box, egg, fox appear 1 time, green, ham, house, like appears 8 times, mouse, Sam, right? So based on these counts, it looks like this document belongs to green, eggs, and ham, right? And probably these ones do not, okay? So just looking at the word counts, can we start clustering these, right? If you look at some of the other columns, some of the other columns are things like, I don't know, hot night, sun 3. Okay, so we have these different word counts for different words. You know, how many times did, you know, in document 11, the word train appeared 6 times. Okay, what about these other words? And so, you know, so we would go through and we would ask it to, and we're going to tell it to start searching for different clusters here. Okay. All right. So anyway, we'll stop here for now, and I will post up at least instructions for the homework, and you can start, just get a look and just start to take a look at it, and just see if we can start to think about this problem of trying to create clusters for our documents based on just the word counts that appear.
Okay, here's a Dr. Seuss book.
Thanks, Eva. We'll start to think about clustering each of these different documents. Oh, do we have a view quiz today? Oh, I guess I do have. All right, let me give you your answers to the view quiz. All right, the answers are A, E, and B. A as in apple, E as in elephant, and B as in bear. And I put them into the chat. A as in apple, E as in elephant, B as in bear. Those are your answers to today's view quiz. All right, thanks everybody. We'll end here for today. I'll have office hours online. And other than that, have a good day, and we'll see you guys on Wednesday.